Good afternoon. I'm J.D. Harrington, NASA Public Affairs Officer for the Science Mission Directorate in Washington, D.C. I'd like to welcome you to today's media conference where we'll discuss the mission and launch of NASA's newest spacecraft, the Wide Field Infrared Survey Explorer, otherwise known as WISE. WISE is scheduled to launch no earlier than December 9th aboard a United Launch Alliance Delta II rocket from NASA's Space Launch Complex 2 in Vandenberg Air Force Base, California. Once in orbit around Earth, WISE will scan the entire sky in infrared wavelengths, unveiling hundreds of thousands of asteroids and hundreds of millions of stars and galaxies. During the next hour, you'll hear what our scientists and engineers have been doing to prepare for this exciting mission. As for the order of events this afternoon, we'll have 5 panelists joining us. Each will give a short briefing, and then we'll open the phone lines for questions and answers. I'd like to take a moment to welcome and introduce our panelists joining us today. First, we have Dr. John Morris, NASA's Astrophysics Division Director at NASA headquarters in Washington, D.C. We have Ned Wright, the WISE Principal Investigator from UCLA. Bill Iris, the WISE Project Manager from the Jet Propulsion Laboratory in California. Amy Meinzer, the WISE Deputy Project Scientist, also from JPL. And Peter Eisenhart, the WISE Project Scientist, also from JPL. And with that, I'd like to hand the discussion off to John Morris. John?
Hey, thanks, JD, and welcome to everybody. We're very excited here to be launching WISE, which is NASA's latest mission in the Explorer program. It will map the entire infrared sky to exquisite sensitivity and will enable breakthrough science. The launch of WISE caps a series of missions that have launched for the NASA's Astrophysics Division over the past 2 years. We had glassed Fermi in June of 2008. The Kepler mission launched last March 2009. Hubble Space Telescope Servicing Mission 4 in May of 2009, and then also the European Space Agency's Herschel and Planck missions, on which NASA is a partner, launched also in May of 2009. All those satellites are up, doing great science now, and we're about to launch WISE. So let me go to the first graphic, which shows our current portfolio of missions. We see along the bottom there, you see Hubble on the right side, Chandra and Spitzer. Those are great observatories. We've added, as I mentioned, Kepler on the lower left and Fermi on the upper right. We also have the international missions that are labeled there, either the European Space Agency or the Japanese Space Agency on XMM, Integral, Suzaku, and then Herschel and Planck, as I mentioned. We also have a very important component of our program, which is the Explorer program, represented by SWIFT, RxTE, GALEX, and WMAP. And now on the next graph, we're about to add WISE. Not shown to scale, although I'm sure Ned would like the 40-meter version of WISE. The 40-centimeter version is what this is, and it's large to represent its newness. Now, WISE is going to do an infrared sky survey, and it's going to add to the scientific capabilities of Spitzer and Herschel in particular, which will be able to do follow-up observations based on new targets discovered in the WISE survey. Hubble will also be used to follow it up, and this sky survey will leave a legacy for scientists to mine in order to support future missions such as SOFIA and the James Webb Space Telescope. Finally, I wanted to mention that WISE is launching here at the end of the International Year of Astronomy. And we've spent the last year, along with many organizations around the world, talking about the excitement of astronomy and astrophysics, its accessibility to the public, and how it generates inspiration for students to go into STEM careers, for example. And WISE has a vigorous education and public outreach program, and many teachers and students will be participating in that. So now let me hand it over to the principal investigator, Dr. Ned Wright.
Thank you, John. So WISE will survey the sky with much improved resolution and sensitivity than previous surveys. This means that WISE will get much sharper pictures and be able to see much fainter objects. And as a result, it will see about a few hundreds of millions of objects. Now, many of these are stars and galaxies, so we can see at other wavelengths, but for millions of them, WISE will be the first time that we've ever seen these objects. So let me just say a little bit about how WISE is going to do its sky survey. So if we have the first animation going, we can see that WISE is orbiting around the Earth, following a path across the line between day and night on the Earth. And as it orbits, it surveys a strip of sky. And as the Earth orbits around the Sun, that strip of sky moves over. And after 6 months, we've completed a survey of the entire sky, giving us a new view of the universe. Now, infrared waves are longer than the waves of optical light. And so WISE is looking at light waves that are 5 to 33 times longer than the waves of red light that your eyes can see. As a result, infrared bands are good for studying cooler objects that are cooler than the sun or light bulb filaments that produce the light we see. Now, all objects that are warmer than absolute zero produce infrared light. And so if we look at the next graphic, you have an infrared picture of me. And the warmer parts of me, that's the skin around my eyes, actually produce the brightest infrared radiation. And the dimmest parts of the picture are where my clothes are blocking the heat from my body. So previous surveys, going back 26 years, have produced a survey of the sky shown in the next graphic. So this is an image of the whole sky, and of course it's dominated by the closest galaxy, which is our own. And because infrared radiation can penetrate through the dust that blocks our optical view of the center of the galaxy, the center is quite bright, as is the plane of the Milky Way. And you can see the Milky Way is very, very flat. So it's a very thin disk that we're looking at. Now you can also see that the dust that infrared can penetrate through is actually radiating infrared light. So you see the diffuse red emission in this false color image. That's actually infrared radiation from dust. And this comes primarily from regions where new stars are forming. So this is an exciting aspect of WISE science. So if we zoom into the galactic center in the next graphic, then we can see that previous surveys have given us a fairly blurry image when you actually look at this all-sky survey carefully. And that's because the camera that took this picture in particular only had 62 pixels total. So obviously nowadays we can do much better. And so with WISE, if we go to the next graphic, you can see the kind of resolution we hope to achieve. WISE actually is carrying 4 million pixels. So that's quite an improvement over 62 pixels. So with this WISE improved resolution, by the way, I should point out this is real data here, but we've actually only observed a very small slice of the sky to date with this improved resolution, and WISE will do it over the whole sky. So WISE will give us a roadmap that will be used by big telescopes. As John mentioned, we have the Hubble, we have Spitzer, we have Herschel, and we will have the James Webb Space Telescope. But WISE will provide the roadmap so that they can visit or point at the most interesting objects in the sky. So WISE is very much like a wide-angle lens, taking an all-sky picture. And the big telescopes are like telephoto lenses. And both are necessary for a skillful photographer. So WISE is going to be taking a lot of data. So we're going to be taking a 4-color image. We have 4 different bands every 11 seconds. And we'll be doing that essentially continuously throughout the duration of the mission. And that works out to millions of images. We will stitch these together to make a panoramic view of the whole sky. And this will then reveal to us many interesting objects. We expect certainly to see many asteroids, stars, and galaxies. But really, I'll be surprised if I'm not surprised by finding the unexpected, because we're going to find things that nobody has imagined yet. And with that, I'll pass it on to Bill Iris.
Thanks, Ned. I'd like to tell you about some of the who and the what of WISE. First, the who. We're a team of astronomers from academia and engineers from academia, NASA laboratories, and industry that came together in 2002 to successfully win a competition to build WISE. We have people from the Jet Propulsion Laboratory where we manage the project and where we will do mission operations. We have astronomers from California Institute of Technology where at the Infrared Processing and Analysis Lab we will process the millions of pictures that Ned just described we're going to take for WISE. We have two major subcontractors who are very important to our project. Ball Aerospace Corporation in Boulder, Colorado built the spacecraft for WISE, and the Space Dynamics Laboratory of Logan, Utah built the instrument for WISE. So I'm going to shift now from who we are. Let me just say one more thing. We are a part of NASA's Explorers program. That program has a long and successful history and is managed out of the Goddard Space Flight Center. We have a satellite model here that I'm going to use to illustrate the basic design of WISE. This is about a 10th scale. The satellite weighs about 1,400 pounds. It's got two major pieces. It's got an instrument, which is basically a telescope within a thermos bottle. I'll tell you more about that in a bit. And a spacecraft down below, which contains all of the functions required to power, control, communicate, calculate the activities of the spacecraft once in orbit. It's got a solar panel that provides all the power we need, about 500 watts in orbit, and a large antenna that will point to the Tracking Data Relay satellite system that NASA operates in an orbit much above us. So on my first graphic, I have a picture of the real WISE. This is the satellite in a test chamber at Ball Aerospace Corporation in Boulder, Colorado, where the satellite was exposed for about 2 weeks to the space environment, the thermal environment from the sun and the vacuum environment of space. The test went very well. There you can see a Ball Aerospace technician hooking up some temperature transducers to the spacecraft, and you can also see, it's sort of obvious, that little red thing there. That's a cover over one of our two star trackers. In fact, WISE is one big telescope and two little telescopes. This star tracker takes images, visible images of the sky, which it compares to images in its computer and relays information to the spacecraft computer as to where the spacecraft is pointing. That's very important for WISE to achieve its objective of pointing precisely at these million places in the sky where it will take its pictures. So in the next photograph, I'm switching gears now to the instrument. Here you see a technician assembling the instrument at the Space Dynamics Lab in Logan, Utah. You're looking at WISE from the point of view of a star. The photon just before it enters the telescope of WISE. You're looking at the primary mirror. It's gold-coated aluminum. Behind it there are 12 other gold-coated aluminum mirrors that image the stars onto the eyes of WISE, one of which I have here. This is a infrared array detector. It's a 1 megapixel array. It doesn't look that much different from your digital camera array if you have a really nice one, a big array and a new digital camera. But it's very specialized. It's designed to convert infrared energy into electrical signals. And so these arrays are behind this telescope that I described, and both the telescope and this array need to be cooled to minus 440 degrees Kelvin so that these objects that our astronomers want to detect can be detected rather than the heat from the objects themselves. We do that by cooling the telescope with a cryostat. And on my next picture, you can see that cryostat being filled with the coolant, which is a hydrogen gas that's converted to liquid and ultimately then to a solid. We have now 40 pounds of solid hydrogen in our cryostat. Some people think it looks like R2-D2 without wheels. It's kind of a funny looking thing. It's a lot of complicated plumbing to do this job. The job is complete now, and so we're ready to go, and we're really excited about it. We're going to move our satellite out to the pad, the launch pad at Vandenberg Air Force Base in California on Friday morning, early in the morning, when the wind doesn't blow, we hope. And and launch no earlier than December 7th this year. So with that, once we're in orbit, we're at about a 320-mile circular orbit from which the astronomers will be making their observations. And Dr. Amy Meinzer, who's our deputy project scientist, will tell you how much fun those are going to be.
All right, thanks, Bill. So I'm really excited to get to tell you about some of the science that WISE is going to do. It's great that we're so close to launch. And as Ned and John have said, WISE is an all-sky infrared survey. So you could kind of think of it as the Google map to the universe. In addition to finding some of the most distant objects in the universe, it's also going to find some of those that are closest to our own home, in our own solar system, and that is the asteroids. So in my next animation, you can see a map of our solar system. It's a bird's eye view. And you can see that most asteroids in the solar system live in the main asteroid belt, which is between Mars and Jupiter, and that's between the red and the purple lines in the graphic. But there are some asteroids whose orbits take them close to the Earth's, and you can see those as the red dots here in the animation. Now, it turns out that WISE is going to be finding about 100,000 new asteroids in the main asteroid belt, and we expect it's going to find several hundred new asteroids that get too close to Earth's orbit, and we call these the near-Earth objects. So these are asteroids and comets whose orbits take them close to Earth's orbit. So 100,000 new main belt asteroids and a few hundred new near-Earth objects. Now, as Ned mentioned, all objects that are hotter than absolute zero emit some amount of infrared radiation. In fact, I'm pouring out infrared light right now as I sit here. And in particular, objects that are close to room temperature emit very strongly in infrared light. So you can imagine that if you take an asteroid and you put it at the same distance from the sun as the Earth, it's going to emit a lot of infrared light. It's going to glow very brightly in infrared. In my next animation, you can see some sample data taken from another NASA infrared telescope called the Spitzer Space Telescope. And this shows 4 frames of actual data of an asteroid. And it's on a loop, which is why it keeps jumping back. But you can see the asteroid stands out very distinctly in the infrared data. It shows up as a red dot that's moving. It's very bright in the infrared, and it looks quite different than the stars in the image. And because it's moving, it's also very easy to detect. So infrared is a very powerful way of finding new asteroids. Now, in fact, Spitzer was only able to survey about 1% of the entire sky in detail. So if you want to find large numbers of near-Earth objects, like the asteroids and comets that we expect to find with WISE, you need to survey a much larger area. And that's what WISE is going to do. So as I said, we'll be finding lots of dark asteroids with WISE. Now I have here 2 rocks. And one of these rocks is sort of a light and shiny color. And the other one is a much darker color, sort of like a piece of coal. To a visible light telescope, the light asteroid over here is going to show up more distinctly because it reflects a lot more sunlight. Whereas this dark object over here, even though it's larger, would appear much fainter to a visible light telescope. But in infrared light, both of these objects look equally bright. And in fact, this dark asteroid over here may stand out more to an infrared telescope because what you're seeing is the heat that's being radiated from the asteroid. So WISE is going to find a lot of these dark, hidden objects that are easily missed by visible light telescopes. So dark asteroids can't hide from WISE. And WISE will also tell us something about the composition of the population of asteroids, both in the near-Earth regime and also in the main belt. It's going to give us some information as to whether asteroids are typically light and fluffy like a marshmallow or heavy metal. So it'll tell us about composition as well as the true numbers of asteroids. So in this sense, because it will help us find the dark, hidden asteroids, and because it's going to tell us about the asteroids' compositions, WISE is going to help us prepare for the future. So we can better plan mitigation campaigns for potentially hazardous asteroids. And with that, I'm going to pass it off to the mission's project scientist, Dr. Peter Eisenhart.
Thanks, Amy. So as we've been saying, WISE is going to observe everything in the universe that's further away from the sun than the Earth is. And Amy's just told you about the objects that come closest to the Earth, the near-Earth asteroids. I'm going to move on out beyond our solar system and tell you about some of the superlative objects that we'll find in the rest of the universe, the closest stars and the most luminous galaxies. So in the next graphic, we see a representation of several stars, beginning with our sun in the upper left corner. And then as we move to lower mass stars, stars become cooler, and therefore they put out more of their light in the infrared wavelengths that WISE is sensitive to. If we go to lower masses still, we get to what's called a brown dwarf or failed star. These are objects that have less than about 8% of the mass of the sun, or equivalently about 80 times the mass of Jupiter. And you can see Jupiter there for scale. It's only a little bit smaller, but much less massive. So these are brown dwarfs or failed stars are putting out essentially all of their light in the infrared, and they're optically invisible. So WISE is going to find lots and lots of brown dwarfs. So if we look at the solar neighborhood as shown in the next graphic, this is a simulation of the neighborhood of the sun using the star systems that we know about now, going out to a distance of 25 light years from the sun. And there are about 100 star systems in this volume of space. You can see that some of those stars are much brighter than the sun, but a lot of them are fainter. Now what's interesting is that from previous studies, astronomers know that there should be roughly as many failed stars or brown dwarfs that can't sustain the fusion reaction, which is what keeps the sun warm, as the fusing stars that we see here, the ones that stay hot and glow invisible light. So of these 100 nearest stars, only a handful of those are actually brown dwarfs. And so there should be lots and lots of more brown dwarfs in there, but we just don't know where they are. Well, WISE is going to survey the whole sky and find these nearest neighbors, as shown in the next graphic, and that's going to transform our view of the solar neighborhood. And it's possible that one of these nearby brown dwarfs is even closer to the sun than any star that we now know of. The closest star that we know of now is called Proxima Centauri. It's about 4 light years away. Brown dwarfs have evidence for planets around them, and so we might also be finding the nearest planetary systems. That's evidence that would come from follow-up observations with more powerful pointer telescopes, such as the James Webb that John mentioned. Okay, I'm now going to leap beyond our solar neighborhood. I'm going to talk about objects that are not hundreds of light years away, not thousands of light years away, but millions and billions of light years away. We're going to leave our galaxy behind and go to a nearby galaxy shown in the next graphic. And this one is called the Cigar Galaxy, also known by astronomers as Messier M82. On the left, you can see a picture of the Cigar Galaxy in visible light. You can see that it's relatively normal looking. It's got a little bit of disturbance, a dust band running across it. But when we go to the infrared view that's shown on the right, which is from data from the Spitzer infrared telescope, you can see that something truly dramatic is going on here. And what's going on, in fact, is that M82, the Cigar Galaxy, is a starburst galaxy. It's forming stars at a very high rate, 10 times higher than our entire Milky Way galaxy, even though this is actually a smaller galaxy than the Milky Way. Our predecessor survey, the infrared astronomical satellite, discovered there's a class of objects called ultraluminous infrared galaxies that shine with over 1 trillion times the light of the sun, and most of that light comes out in the infrared. And these are super starburst galaxies that are forming stars at a rate that's even dozens of times higher than the Cigar Galaxy, maybe even hundreds of times higher. So these are really cataclysmic galaxies in formation. They're rare today, but from studies with Spitzer, we actually know that they were much more common 10 billion years ago when the universe was 3 or 4 times younger than it is today. Now, WISE has been designed so that it can detect these cataclysmic, dusty forming galaxies out to a distance of 10 billion light years over the entire sky. So we're going to find the most super duper, hyper, ultra luminous forming galaxies in the universe, and we'll see just how extreme this forming galaxy process can get. And these are also going to be the most rewarding objects for follow-up studies with more powerful pointer telescopes, such as upcoming Sophia Herschel, which is in orbit, and the upcoming James Webb. So to sort of wrap things up here, WISE is going to carry out a sensitive infrared map of the entire sky, and it will allow us to learn lots of things about the objects that we already know about and find even more superlative examples, the closest stars, which I've described, and the most luminous galaxies. But perhaps the greatest benefit of an all-sky survey is that you can keep coming back to it. There are objects that are likely to be discovered years after the WISE survey is complete. And if you want to know the infrared properties of those objects, you can come back to the WISE survey, and the catalog and Atlas will tell you all about it. There are papers, hundreds of papers being published today by astronomers based on the infrared astronomical satellite survey 25 years ago. Still, every year we get hundreds of new papers that refer to that survey. So that's why we like to say that the legacy of all sky surveys endures for decades. Thanks.
Thanks, Peter. And you've heard from our panelists. Now we'll open to the question and answer portion of our briefing. If we could have the media start by identifying yourself, your media affiliation, and if possible, please target your question to a specific panelist, if at all possible, to eliminate any confusion. And for those on the phone bridge, if you have a question, push the *1 keys on your telephone to let the operator know that you have a question. With that, do we have any questions here in the audience? Okay, we have somebody online from JPL. Go on, you're on.
Hi, this is Emma Gallegos from the Pasadena Star News, and I just wanted to know more about what the budget is for WISE.
I'll take that. The budget for the entire WISE project is about $320 million. That includes the development of the satellite, the development of the mission operations, the execution of the mission operations, and the launch vehicle.
All right, thank you. Our next person on the phone is Ann Ryman from the Arizona Republic.
Hi, thank you. I was wondering if you could talk a little bit about how big this satellite is in terms that people could understand, if it's, I don't know, the size of a car or a bus, and then how far up in our orbit will it be? Like how many miles up will it be?
I'll take that one too. Our media guide says it's about the size of a polar bear. Now, most of us don't run into polar bears, fortunately. The analogy I like is it's about the size of a race car, and it's more sort of, I compare it to a race car. It's a very highly efficient machine, custom machine, about 1,400 pounds, so it's a small car. That would also be a reasonable analogy for people's daily experience. As far as the orbit, it's 325 miles above the surface of the Earth, circular, and it runs along the day-night terminator, so it's sort of looking at sunset, sunrise continuously.
All right, do we have any other questions here in the audience? Okay, well, then we're going to go ahead and conclude today's media conference. I'd like to thank the panelists first off before we close. Appreciate your time. And if you'd like more information about WISE, by all means, join us on the web at www.nasa.gov/WISE. Thanks for joining us today, and have a great day.